Today I'd like to talk about specific heat and heat capacity. So far we've been talking a little bit about the relationship between heat and temperature, and I've made a big deal about how heat and temperature are not the same thing. In particular, heat is a transfer of energy from one system to another. Temperature is a property of the system itself. And furthermore, you probably recognize that there's something weird going on because in an isothermal process, the temperature of a system doesn't change, but heat is being added. So they're not exactly the same, heat and temperature, but nevertheless, there is some relationship between them. You have a sense that if I add more heat to a glass of water, its temperature will go up, and so there's some relationship there. So that's what we want to get to today. That relationship between heat and temperature is provided by this concept of what we call specific heat and heat capacity. Okay, so in general, when you add heat to a substance, its temperature may go up. Not always. Like we talked about in an isothermal process, the temperature doesn't go up. But sometimes it does go up. For example, when you heat a glass of water on a stove, the temperature goes up. So the question is, if I add a certain amount of heat, how much does the temperature go up? And the relationship between those two things is provided by this thing called heat capacity. So let me write an equation like this. dq is equal to capital C times dt. This is a relationship between heat added. So remember, dq is the infinitesimal amount of heat added, and then dt is the infinitesimal change in temperature. And the proportionality constant between those two things is called the heat capacity. So this is a capital C. It's called the heat capacity. By the way, you can check that the units of C are pretty clearly joules per Kelvin, because the thing on the left side, heat added, has units of joules, and the thing on the right side, dt, has units of Kelvin. So the units of C must be joules per Kelvin. Basically telling you, how much heat do you need to add in order for the temperature to change by 1 degree Kelvin. That's what the heat capacity is. Now, I should mention that heat capacity is a terrible name. It's a terrible name for this quantity because remember, an object doesn't have heat. It makes it sound like it's the amount of heat that the object can hold or something, which is totally not correct. So this is just something that we're stuck with, but for historical reasons. People started calling this like a couple hundred years ago, and we kind of are stuck with it now. So it's a terrible name. Don't get confused. It's not in the amount of heat that an object can hold or something like this. It's the relationship between the amount of heat you need to add in order to change the object's temperature by 1 degree Celsius, let's say. So we're stuck with this. For historical reasons. C is what we call an extensive quantity. And what that means is it scales with the size of the system. I hope it's kind of obvious that if you take 1 joule and you dump it into a glass of water of heat, so you transfer 1 joule of heat into a glass of water, its temperature is going to go up by some amount. If you take 1 joule of heat and you dump it into Lake Ontario, its temperature is going to go up hardly at all because Lake Ontario is so much bigger than the glass of water, right? So a bigger object, an object which has more stuff in it, more mass, has a larger heat capacity than the smaller object, which is made of the same stuff. So this, that's what we mean by an extensive quantity. It scales up with the size of the system. A lot of times you want to know property of the substance itself. If I take a glass of water and I add 1 joule to it, its temperature increases by a certain amount. If I take Lake Ontario, I add 1 joule to it, its temperature increases by hardly anything. But those two things are both made of water, and I would like to somehow get rid of the dependence on the size of the system. I would like to talk about the property of water, which is related to how hard it is to change its temperature. And that's what we call the specific heat. So specific heat is a property of the substance. And I can get that by dividing out the heat capacity by the mass of the substance. So it's heat capacity per mass. Okay. So the specific heat is the capital C divided by the mass of the substance. Now in this class, you notice I'm using the capital letters for the extensive quantities and the small letters for the intensive quantities. Those are quantities which don't depend on the size of the system. Specific heat is what we call an intensive quantity. It doesn't depend on the size of the system. So extensive quantities depend on the size of the system. Intensive quantities don't depend on the size of the system. And I'm using here again the relationship that the small letters are intensive quantities. So those are things which don't depend on the size of the system. And the large letters are extensive quantities, which depend on the size of the system. So let me remind you of the importance of the small letters and the capital letters. When we were talking about volume, we had the small v was the capital V divided by the number of moles. The small v is intensive, doesn't depend on the size of the system. So this is the intensive quantity. And then the capital V is the extensive quantity. So just a reminder, V is equal to what we call specific volume. Small letters are related to the capital letters by dividing by the number of moles. We have the same thing with energy. So internal energy U, specific internal energy, is the capital U divided by the number of moles. U is the specific internal energy. Okay. So now you see why we call it specific heat. It's like the intensive quantity that's associated with heat capacity. Okay, now a little bit of notation. You'll notice that normally I get the small letters by taking the capital letters divided by the number of moles, right? I did that for volume and for internal energy. But the notation typically is that the small c, specific heat, is found by taking the large C divided by the mass, which is not the same as dividing by the number of moles. So I'm going to use a different notation here, which is called molar specific heat. And that's going to be Cm. I'm going to put an extra m there, is the capital C, the heat capacity, divided by the number of moles. Okay. And this is generally the quantity that I'm going to be focused on in the class. So molar specific heat, for me, I wrote an extra m there to remind you that's the heat capacity divided by the number of moles. Let me provide a word of caution here. If you're reading the textbook, in Carter's book, he uses C means molar specific heat. But that is so non-standard. In almost every other textbook, the small c means specific heat, heat per unit mass. So that's why I'm not going to do that. I'm going to always write this extra m here. So my molar specific heat has the m there to remind you that's the heat capacity divided by the number of moles. The small c is the specific heat, which is the heat capacity divided by the mass. So there's lots of c's floating around. You got to try to keep them straight. So remember, capital C, heat capacity. Depends on the size of the system. The units of capital C are, like we said before, joules per Kelvin. The small c is specific heat. So the units of the small c are joules per kilogram times Kelvin, right? Because it's the heat capacity divided by the mass. And then the molar specific heat which I'm calling Cm, has units of joules per mole times Kelvin. Some more notation. So remember we had this. Right? So in other words, the amount of heat that I need to add to change an object's or a system's temperature by 1 degree is what we call the heat capacity. And sometimes this is normally written like this. So just divide the dt to the other side. Heat capacity is dq divided by dt. Okay. Now, point of really confusion is that a lot of times students think this is a derivative, but it's really not a derivative. That's why that funny dash is on the d there. Just to remind you that q is not a state variable. So caution, this is not a derivative. It's not a partial derivative. In other words, a lot of times students will say, oh, okay, I get the function q, which is maybe a function of t and v, and then I take the derivative. This is wrong. The reason is there's no such function, q is a function of t and v. Q of t and v does not exist. It's not a state variable. So q is not a state variable. Okay. So it's better to think of this in terms of like, what does this actually mean? It's not the derivative of the q function, because there is no function q. It's a small amount of heat added divided by the small amount of temperature change that results from that heat added. Okay? Okay, so watch out for that. Now let's write similar things for the heat, specific heat and the molar specific heat. First of all, you'll see often, generally in the course, the small letters Q is the large letter divided by the number of moles. So this is the heat added per mole. Okay. So I can write, let's take my relationship here, C is equal to dq divided by dt. The capital C is the small c times the mass of the object. And the capital Q is related to the small q, so I'll put here d times the small q times the number of moles, dt. Now the number of moles is constant, so I can, let's rewrite this. C is equal to the number of moles, which I can bring outside, divided by the total mass of the object, dq divided by dt. And this is the molar mass. So C is equal to the total mass divided by the number of moles. That's 1 over the molar mass of the object, or of the substance, dq dt. Okay. Finally, let's write this in terms of the molar specific heat. So C is equal to the molar specific heat times the number of moles. So that means Cm times the number of moles is equal to dq times the number of moles divided by dt. And here the number of moles cancel. So you have here Cm is dq divided by dt. So we have all these relationships here for heat capacity, specific heat, molar specific heat. So you got to try to keep all these things straight. And the easiest way to keep them all straight is by watching the units. Heat capacity, how much heat is needed to change the temperature of a system by 1 degree Kelvin. Specific heat here, how much heat must be added in order to change 1 kilogram of the substance by 1 degree Kelvin. And molar specific heat here, how much heat is needed in order to change 1 mole of the substance by 1 degree Kelvin. Okay? So hopefully you have all these different quantities straight now. Heat capacity, specific heat, molar specific heat. So a little just concept question for you to answer. Two equal mass liquids initially at the same temperature are heated for the same time over the same stove. You measure the temperatures and find that one liquid has a higher temperature than the other. Which one has the higher specific heat? So is it the cooler one, the hotter one, or both the same? Go ahead and pause the video and see if you can answer this question before going on. So hopefully you have answered the question in your mind. You have idea for which one is the correct answer. The answer is the cooler one has the higher specific heat. Because remember, dq is equal to C times dt, right? Now the heat added is the same for both, right? Because they're heated on the same stove for the same amount of time. So that means that the heat capacity for object 1 times the change in temperature for object 1 is equal to the heat capacity for object 2 times the change in temperature for object 2. Now heat capacity is the specific heat times the mass. But they are telling you that the mass is the same. So where the temperature change is larger, the specific heat will be smaller. And when the specific heat is larger, the temperature change will be smaller. In other words, I like to think about specific heat and heat capacity as being a measure of thermal inertia. So C is a measure of thermal inertia. How hard is it to change an object's temperature? If C is large, it means it's pretty hard to change the object's temperature. If C is small, it's pretty easy to change the object's temperature, or the substance's temperature. You can take a look at specific heats of particular quantities. So on the right, you see a table with the specific heats of various substances. Joules per kilogram degrees C. It's of particular interest that water has a very high specific heat, which is good. Compared to everything else, water's the highest thing on here. That's good because we're made mostly of water, and we want our temperature to be roughly stable. Right? If water had a very low specific heat, then if we absorbed a bit of heat, our body temperature would change by a huge amount, which is not good, right? So the fact that water has a very high specific heat means it's pretty stable. It's very inert, thermally inert. It's hard to change its temperature, which is good for life because it's a kind of stabilizing factor. There's an additional complication that we need to discuss, which is related to this question that I just asked. So how about this question? Two pans each contain the same amount of water, and they start at the same temperature at 20 degrees Celsius. But both pans were heated until the water reached a temperature of 94 degrees Celsius. One of the pans is left open while one has a tight glass lid over it. So you might think, well, okay, well, that means that they're both water, right? And if we put it on the same, the change in temperature is the same. So doesn't that mean that the heat added is the same? But there's a problem with this reasoning. in particular, you probably have some experience with this. Like if you're going to boil water on your stove at home in your kitchen, the fastest way to do it is by putting a cover on it. So you know that when I put the cover on it, it's somehow easier to change the temperature of the water. It's on the same stove. Whereas if I don't put the cover on it, it's harder to change the temperature. So why is that? That's what I'm going to have you think about as a kind of, I'll leave you with this question, and we'll come back to this question during class. Okay, so in this little short video, I've discussed the relationship between heat and temperature. That relationship is provided by this thing called the heat capacity. The heat capacity depends on the size of the system. But then there's two things that you can do to discuss the property of the particular substance under consideration. That's the specific heat. You can divide the heat capacity by the mass, or the molar specific heat, which is where you take the heat capacity and divide by the moles, number of moles, right? So heat capacity, specific heat, molar specific heat, all three of those things are things that we use to describe the relationship between heat and temperature. And we talked about how something which has a large specific heat or a large heat capacity, it's hard to change its temperature, whereas something if it has a small specific heat or a small heat capacity, it's easy to change its temperature. So specific heat is kind of proportional to thermal inertia, how hard it is to change the temperature of the substance. We'll pick it up there. There's some additional complications, which is that, in fact, you're going to have to talk about how exactly are you heating the substance, under what conditions. That will tell you the amount of temperature change. So I hope you found this useful. Thanks for your attention, and see you all in class.